What? That's such a bad UI because it's like I thought it was good.
Okay. So what do you think? Was that easy to define? Who says yes? Ish. We've got a hard yes there. How about no? No. Okay, well let's see what you come up with. Okay. All right, hard yes. What do you got?
Machine interpretation of data.
All right. It's not bad. So what does interpretation mean?
To take the data and have an output.
So take in data and have an output. So like a calculator.
Yeah.
It might be. It really might be. Okay. You.
Automation of learning and making decisions.
Automation of learning and making decisions. My PhD is not in spelling, so you'll have to forgive me for that. That's good. Okay, so automating learning and making decisions. That's a reasonable one. How about you?
Includes but not limited to solid state machines.
Well, we've got some fine text. Okay. Includes but is not limited to. You said finite state machines.
Finite or solid state machines. Yeah.
Or solid state machines. Did you say solid?
Yes.
All right. Okay, so if it includes solid state machines, then you're correct. But there could be more to the story. How about you?
A machine that learns, sometimes adapts, and reacts.
Okay, that's great. Sometimes adapts and reacts. Okay. Anybody else? Anything that's wildly different? Maybe? Yes?
This might be a little on the sci-fi side, but
sure.
Simulated sentience.
Simulated. Ooh, that. How do you
I don't know.
Sentience.
Put 3 question dates. Okay. All right. So what does it mean though to be sentient, spelling aside. Aware of itself. Okay, so that's tough. I think we're getting philosophical, which I really like. Yes.
Every time we break the bounds of sentience, we redefine it a little further ahead.
So we don't even know what the definition is right now. That's great. It's going to be a tough class. Okay.
Lots of psychologists define it as an ability to self-reflect. Like we think African gray parrots are sentient because they can ask, "What color am I?"
Okay.
Asks, "What program am I written in?"
Okay, so it self-reflects. But if I just write a chatbot that asks that question because I hard coded it in, thumbs down. Okay, that may not work.
Now we're in the Chinese room.
So this is, I guess, the point of this is that it's tough to define what artificial intelligence is, and there's many schools of thought. A lot of them are detailed in the reading I didn't tell you about, but you should do. And so we're going to kind of define this as we go, but maybe it's one of those you know it when you see it type things. But to get some more insight, let's go back and kind of look at what AI has been historically. So in this class, we're going to go a little bit over kind of the history of AI before we get into the modern stuff. So AI has been something that people, the species, have been thinking about for a long, 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 long time. This image on the lower left is Talos, which is, I believe, ancient Greek, 400 BC, a legend of an artificial machine. There's golems shown in the middle. We have more modern, if the 18th century is more modern, the Mechanical Turk there on the right. Has anybody heard of the Mechanical Turk?
Yeah.
So Mechanical Turk, if you're not aware, was the first chess-playing AI, and it was really good, especially for the 18th century. So this robot-type thing would sit there and it would play chess against you. It would move its arms and move the chess pieces. And it was beating a lot of people at chess, which seems strange because it feels like we didn't solve chess until pretty recently in AI. So what happened here? Well, it turns out that there's a person inside that who's really good at chess. So maybe it doesn't count. I don't know. But interesting story. Okay, so very early days of AI we may consider to be like the 40s and 50s. And so in the 40s and 50s, people started thinking about neural network computers. So if you think that deep learning and neural networks are something that only came around in the last however long you've been in school, you've been misinformed. It came from the 40s and the 50s. It didn't work very well yet. For instance, in 1951, they built the first neural network computer, but it required 3,000 vacuum tubes and a surplus autopilot mechanism for a V24 in order to simulate a network of 40 neurons. So maybe we weren't ready yet. In 1950, Alan Turing, have you all heard of him? He wrote a paper called Computing Machinery and Intelligence. This was a seminal paper, and it introduced something called the Turing test. Raise your hand if you've heard of the Turing test. Okay, a lot of you. So the Turing test is basically a test for is this system intelligent or not? And it asks the questions, can machines think? Can they behave intelligently? So this is called the imitation game, Turing test. And basically the way it works is you have some human interrogator, and this human is interacting with some agent via text. And that agent is either a human or an AI system. And if the human interrogator can't tell the difference, then the AI system passes. So if the AI system can fool the human, then it's passed the Turing test. And it was predicted that by the year 2000, there'd be a 30% chance of fooling a layperson for 5 minutes. Not terribly crazy. It did suggest some of the major components of AI, things that we think about today. What is knowledge? How do we represent it computationally? What is reasoning? Can you reason over the knowledge that you know? Can you understand the input? You have to understand the language of the interrogator. Can it learn? There's some problems, though, with this concept. It's not really reproducible because it kind of depends on the person. Some people might be more easily fooled than others. You can't really do rigorous mathematical analysis on this. And there's some other problems. Can anybody think of other problems associated with this? Yes?
Well, it's heavily based on the interrogator. If you have a different interrogator, then it would be different outcome.
Absolutely. Yes?
The human might be actively trying to act like AI.
Sure. Yeah, we don't really have, at least in this summary, a description of what the human's supposed to be doing. Yeah, it's kind of subject to that kind of antagonistic behavior, right? Yes?
philosophically, it's not clear whether being able to imitate a human really counts as consciousness or thinking in any deep sense.
That's a great point. Is imitating how a human is intelligence the right answer for intelligence? In many cases, it may not, right? Yes?
The results can be really dependent on the context, like what situation the interrogator's in. Do they know that they're trying to figure out if something is an AI? Do they not? Like, what's their
Sure.
intention? What's their base knowledge about computers in general?
Right, and that kind of points to some problems that have been identified with this. For instance, if the AI system spells too well, this is something dear to my heart, obviously, then it gives itself up. So people have created systems that intentionally misspell words in order to better fool the human. You better be careful about how you're asking questions. If the human interrogator, on your point, says, what's the square root of 256,971, and you know, right then you're probably not the human, right? So, but is that really? Maybe you are. I'm certainly not. So people are building in these heuristic checks, like don't be too computery, right? Things like this. That kind of goes counter to the point of the whole exercise, right? So there are some issues with this, but it's a very, very foundational, fundamental concept, and starts to define the field. So in the 50s and 70s, they call this the look ma no hands period. Computers in the 50s and 70s were not very powerful, so anytime they did anything that seemed useful or remotely intelligent, it was really exciting. So this includes things like programs that play checkers at an amateur, like a good amateur level. Things that started to look at logic and proving theorems, or proving geometry proofs, things like this. In 1954, they developed the first programmable robot arm. Robotics is a big kind of co-field with AI, so we'll talk about robotics a lot here. They developed Lisp. Has anybody programmed in Lisp? Oh, you're missing out. What a great thing. You should try it sometime. Anyway, I love Lisp. Anyway, a lot of early AI research was done in Lisp. It's the second oldest programming language in current use, excepting Fortran. Yeah, and also this is intelligence be carried out during the summer of 1956 at Dartmouth. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. It's pretty bold, it seems like, but that's what they said. And many of the founders of AI were there, including these very important, very famous people. One of these attendees, Herb Simon, said in 1957, "It's not my aim to surprise or shock you, but the simplest way I can summarize is to say that there are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly into a visible future. The range of problems they can handle will be coextensive with the range to which human mind has been applied." Which is also bold. And when pressed, said more precisely, within 10 years, a computer is going to be a chess champion, and an important new mathematical theorem is going to be proven by a computer. So those both happened. It took about 40 years instead of 10. And it does highlight kind of something that's been true about the field of AI for a long time, and that's that it's very difficult to identify how long things are going to take. And there is the tendency, perhaps, from maybe researchers in the field or popular science publications and things like this, to kind of get people excited about things that are maybe a little harder than they seemed at first glance. Okay, continuing on. So, in the 70s and 80s, we had something called knowledge-based approaches. And this is where we really started to say, what does it mean to know things, and how do we relate these concepts computationally? Something important to me, in 1970, Shakey was developed by the Stanford Research Initiative, I believe is what SRI stands for. And this was the first intelligent robot. So let's look at what Shakey is. Let's see.
Shakey was the world's first mobile intelligent robot, embodying numerous breakthroughs in artificial intelligence, robotics, computer vision, navigation, and other research areas. The robot was developed from 1966 to 1972 by SRI International, then called Stanford Research Institute, and its legacy and impact are still very much alive today.
Shakey's really the great-grandfather of things like self-driving cars and even military drones.
The hardware was really pretty primitive, but the software architecture and the software algorithms are what changed the world.
I think we all thought we were doing really interesting stuff, so it didn't really dawn on us that we were doing anything special.
Shakey established a position about what we should be thinking about as possible, as feasible.
To understand why Shakey is so important, we have to go back to 1966, and we have to understand where AI research was at that time.
Well, you have to remember that it was pretty much of a greenfield when Shakey started. All over the country, and even outside of the United States, people were beginning to build the components to artificial intelligence. Nobody had tried at the time that Shakey was launched to integrate all the components of AI and robotics into a single moving vehicle that could reason about the world, could sense the world around it, and could take actions.
Prior to 1966, there were no robots, or at least not intelligent ones. The concept of an intelligent robot was limited to the realm of fiction.
You will meet a charming character in the robot, always.
When you read the title of the original proposal, it was something like a mobile automaton for reconnaissance. And the reason we called it an automaton was because until Shakey, you couldn't go to a funding agency and say, I want money to make a science fiction kind of device. And so we needed a name, and finally Charlie, in his inimitable fashion, said, it shakes like hell when it moves, let's just call it Shakey.
Key components of Shakey's hardware were a TV camera to observe its environment, an antenna radio link, bump detectors, and a push bar to move objects.
My role was mainly get the images and get whatever coordinates they needed to determine where they were and extract the information from the image. I remember when I first saw it, gee, that looks like a dishwasher, on wheels.
While charming, Shakey wasn't impressive for its looks. It was the AI and programming advancements that made it famous.
We structured Shakey software in 4 distinct layers. And that was the first time that a layered architecture was used for robots.
Shakey's pioneering software architecture paved the way to a new era of AI and robotics. The SRI team later developed Flaky, a research robot that demonstrated fuzzy logic and goal-oriented behavior. Then came Centibots, one of the earliest projects in swarm robotics, where 100
numbers into other numbers, you get to see the thing come to life right next to you.
Shakey also inspired research in natural language-based interactions, leading to the popular speech-based technologies that we use today. Shakey's breakthrough in computer vision is now used to help drivers stay in their lanes. And every time you get driving directions on your phone or a navigation system, you are benefiting from the A-star navigation algorithm, first invented for Shakey. Even NASA's Mars exploration rovers use navigational techniques that were first launched with Shakey.
The future is things like potentially having teams of autonomous aircraft that could go out, for example, and do firefighting, and doing this either fully autonomously or potentially in tandem with human-piloted aircraft that can go out and work with them collaboratively.
Shakey now resides in the Computer History Museum, visible to hundreds of thousands of visitors annually. And in 2017, Shakey was honored with an IEEE Milestone Achievement Award.
The Shakey milestone is important because, first of all, Shakey is the world's first mobile intelligent robot. In addition, this is the first IEEE milestone in the areas of either robotics or artificial intelligence.
Looking back, more than 50 years after the Shakey project began, it's inspiring to see how one small team can make such an impact. How one ambitious idea continues to benefit our lives. How one robot changed the world.
We didn't realize, I think, any of us, what the significance of this was. We knew we were first, but nobody knew where it was going, and I don't think any of us would have predicted what happened.
Shakey planted the flag way out there. It's a model of the kind of ambitious projects that we should be looking at in the future.
So, this was really groundbreaking work, and as a part of this work, a lot of the problems that define a lot of the areas of research in robotics and artificial intelligence were explored for the first time. So, that was very interesting. In the 80s, let's try this again. Okay. We then had kind of the AI boom in expert systems, where we had things like automated medical diagnosis tools and things coming out, a lot of excitement about what AI could be, and then that didn't work out so great. So there was a lot of over-promising, under-delivering, and then funding agencies, both public and private, stopped funding AI research in a large part. And that kicked off what we call the AI winter. So then, because of advancements in the computational methods that we use, statistical approaches, probability, a focus on uncertainty when AI systems are encountering and acting in their environment, starting in the 80s, we started to get a little better again. So agents and learning systems were doing much better, and this kicked off the AI spring. So where are we now? Now is in the last 20 years, and more recently the last couple years. So let's talk about what AI can do today. So this is a little quiz, show of hands type experience. So can AI right now play a decent game of table tennis? Who says yes? Who says no? Ah, so you guys watch YouTube also. So yes. It can. Can it drive safely along a curved mountain road? Who says yes? And who says no? We'll say yes for this, but there are some caveats. Can it safely drive up to Alta in a snowstorm? Who says yes?
Well, it depends on what it's driving, right?
What's driving safely?
Very, very good question. How bad is the snowstorm? Great question. So the point of this is that there's still advances to be done in self-driving cars, although we've come so far very recently, and I have a bunch of friends in the valley who are going to be really bummed if this doesn't work out. But there's still a little ways to go, right? Can an AI system buy a week's worth of groceries on the internet? Who says yes? Who says no? Yes. Can it buy a week's worth of groceries physically at Smith's, though? Yes? No? Nobody knows? I'm going to say no, but we're getting really close in robotics to this type of thing as well. How about discover and prove a new mathematical theorem? Who says yes? Who says no? Who's mad at me for using the word discover? Okay, yes. So, can it prove theorems? Yes, absolutely. There's been a ton of really, really exciting work in theorem proving happening. Can it discover new theorems? That's more difficult, right? Yes?
It's been done on accident.
Sure.
I wouldn't say it had the goal to discover a thing, but it's definitely discovered tons in mathematics on accident.
Right. Yeah, so even as you go through, you start exploring what the space, based on your logic system, what is true, right? You start discovering things, but the question is, are you discovering things people care about? That's more difficult, right? Sorry, I interrupted you. What were you saying?
I was going to say it's also helped make new video game designs.
Absolutely. Yeah, so there's been generation of video games being done by AI. Interesting games that people like to play. Very interesting stuff. Can an AI system converse successfully with another person or an owl? It does successfully mean no. Can an AI system perform a complex surgical operation on a person? Who says yes?
They did surgery on a grape.
And the grape people were very excited. Let's talk about on humans. Yeah, I have seen that. That's great work. Can Is this happening right now, do you think? Is the technology there?
Technology's there, I think.
Ethics, somebody said ethics, that's a great point. Kind of. So this is actually one of the things that my research is in automating surgical subtasks and doing shared autonomy in surgery. I do robotics and AI and robotics and medical applications are what I do specifically. And so there are systems that perform some aspects of surgery. I would say that there's nothing that start to finish can perform surgery right now, and it's probably a long way off. But it's an interesting thing, and in the very near future, aspects of this are going to be helping physicians with helping people. And depending on your definition, there are also things in use right now, things that are doing surgical image guidance, for instance, showing physicians or helping them identify where in the body they are, and things like this that are very interesting. So we'll say not quite. Can an AI system unload a dishwasher and put everything away?
Yes.
If the dishwasher and dish holder is built for it.
Good point. So how does it do in novel environments with novel equipment? In unknown environments with a bunch of cats and babies and your grandmother running around? Is it able to do it successfully there? Probably not yet. Is a dishwasher an AI system?
Yep.
No? Yes? I don't know.
Totally.
Can AI translate spoken Chinese into spoken English in real time?
Yes.
Yes. This happened pretty recently. Well, it's much more successful. Did you all see that ad that Microsoft put out recently?
Yeah.
If you haven't, we're going to watch it.
We will prepare for next week's order. We ordered 10,000 units.
That sounds good.
Pretty cool, huh? You're speaking mom in Japanese and mom hears some English.
For next year.
Absolutely, we can put a plan in place.
Do you understand me?
Yes, I can understand you.
Okay, I have a lot of questions. How do you guys fly? What does Santa do in the summer? What's this sleigh made out of? It seems pretty heavy. Is Mrs. Claus a good cook? Do you guys get me? What's your ice cream?
The dog just said he wasn't his son.
So the point of that is that we're actually right now in a pretty exciting time in AI, in that a lot of things that have traditionally been very, very difficult or haven't worked as well as you would actually want them in order to use them are starting to work. And so that's all I want to say with that, is that it's a very exciting time. Can an AI system write an intentionally funny story? You have a question or you say yes?
Only if it's absurdist.
Okay.
Yeah.
My favorite kind. I agree with you. But it has to intend. What does that mean? I don't know. We'll talk about it. But let's say for now, not very well. So what does it mean to write an unintentionally funny story?
The same text prediction that you find on your smartphone when you're texting, and why back the use of a browser story as a backlog to reference from, I'll just leave the video.
I think that's a great point. That what it means to be unintentionally funny is different for different people. It's one of those other things that we know when we see it. There are many ways to do it. Your autocorrect on your phone, for instance, may write an unintentionally funny story. Well, in the 80s, there was a system that was designed to create stories that people would like, an AI system. So here are some of the stories they wrote. One day, Joubert was hungry. He asked his friend, Irving Bird, where some honey was. Irving told him there was a beehive in the oak tree. Joe walked to the oak tree. He ate the beehive. It's so close. Henry Squirrel was thirsty. I like the names. He walked over to the riverbank where his good friend Bill Bird was sitting. Henry slipped and fell in the river. Gravity drowned. That's sad. It's a sad story. Depending on how you look at the sentence "gravity drowned," though, it's correct. Right? Gravity drowned Henry Squirrel. It's not really how we look at things, though, right? Once upon a time, there was a dishonest fox and a vain crow. One day, the crow was sitting in his tree holding a piece of cheese in his mouth. He noticed that he was holding the piece of cheese. He became hungry and swallowed the cheese. The fox walked over to the crow. What is this even about? What is this?
It looks like it's a story. It's a very
It is. It's kind of meandering. There's a lot going on. I mean, I thought the cheese was the point, but maybe the fox walking to the crow was the point.
You know, the fable like this goes that the fox compliments the crow and tricks him into dropping the cheese. Doesn't mean the flatterers are not to be trusted.
So this may lend insight then into where they got their data, maybe where they were learning about how stories work. Very good point.
Give it to an English professor, they'll go at it.
Yeah, they might have a lot of these, maybe a psychologist, I don't know. Why is the fox dishonest? Oh, because it came from the fable, like you said. Very good point. There also were, more recently, AIs that did try to write intentionally funny jokes. So I had an X on the slide, but maybe it's closer. So in a paper called Unsupervised Joke Generation from Big Data, they tried to write jokes of the form, I like my X like I like my Y, Z. This kind of joke. For example, I like my relationships like I like my source. I like my comics. I'm going to change this slide next time, but they found that while human jokes are funny 33% of the time, which may be generous, depending on who you're talking to, the computer jokes were funny about 16% of the time. So we're making progress. So these examples are a part of kind of a related field, or maybe a subfield, depending on how you define it, called natural language processing. Has anybody done any study of natural language processing?
Text to speech.
Text to speech, for instance, yeah. So it's a big field. It covers things like automatic speech recognition, so taking spoken word and translating it into text. Text-to-speech synthesis, which goes the other way. They take a language that's spoken English commands to a robot, and they translate it into the robot's language of action. So they use models that were developed to translate English to French, and instead use it to allow a robot to understand commands from humans. Very interesting stuff. Information extraction, information retrieval, question answering. Not only just hearing words and writing them down, but actually coming up with an understanding underneath the hood of what it means, what these relationships are, what your context was when you said it. Things like this. There's also computer vision. Has anybody done any work in computer vision? Awesome. Very, very exciting field. This is taking as input some signal, generally maybe a video or a still image like this, and determining meaning from that image. Yes?
How is that program distinguishing the airplane from the building behind it?
How is it doing so? I'm not sure. I'm not familiar with this paper exactly, but that's a hard problem, right? That does highlight why this is a hard problem, because a lot of things look the same. But were you driving through that field as a self-driving field driver, you'd want to know that there was an airplane there, right? And not that it was part of the building that was further away. So you also want to take this and determine what's going on in the image, but what it means. The airplane's not flying. That's worth knowing. You can then take understanding of this and ask questions. Is this airplane broken? Is that why it's not flying? Is that Suzanne? I was looking for Suzanne. This kind of thing. We'll also talk a lot about robotics. So robotics, as I mentioned, is kind of this adjacent field. It's a huge interdisciplinary study. A lot of it is done kind of in the mechanical engineering and other engineering domains. This is things like mechanical design of robotic systems, sensor design, things like this. We're not going to touch on that aspect of robotics at all in this class, but a lot of robotics does fall into AI. So taking a robot, having it sense its environment, make smart decisions, enact some change on its environment in order to accomplish some task that's useful to you, that's AI. We find in robotics, I mentioned that I'm a roboticist, that reality, physical systems is much harder than simulation. So in simulation, you have maybe full knowledge of your world. Maybe there's not as much noise. In reality, maybe there's noise in your sensor. Maybe what you thought was true is not true anymore. Maybe you have noise in how you actuate your robot. Maybe it slipped and fell. Things like this you have to be able to account for. Things that account for those are generally AI systems. This has a lot of interesting technological application domains. Things like self-driving vehicles, automatic rescue systems. There's a ton of robots that play soccer, one of the more important parts. And then other automated robotic systems. We'll also talk in this class about logic and logical systems. This will be things like theorem provers. So for instance, on the right, we have a picture of the Robbins conjecture. This is a very famous theorem proving example. This was a conjecture that the mathematicians hadn't proven and is one of the first examples of successful automatic theorem proving. And the interesting thing about the proof of this that the AI system came up with is that it was human readable, and that it didn't take a million steps of very obscure algebraic manipulation. It was pretty short. It made sense. Once the humans saw it, they said, oh yeah, that's great. Which is interesting, right? Because is the output of the AI systems that we talk about supposed to be interpretable by the human? This is an interesting question. Maybe so, maybe not. People have used these logic-based systems for things like fault diagnosis. NASA does that, question answering. Some of the methods we'll cover are reduction systems, constraint satisfaction, satisfiability solvers. Huge advances have happened in these areas. Decision making. So a lot of AI falls under the umbrella of decision making. Scheduling, things like routing airplanes, or doing logistics scheduling for military applications. How do you get all the supplies to all the places they need to be on time? Automatic medical diagnosis, help desk, fraud detection, spam classifiers. We appreciate that, I'm sure. Search engines, book recommendations, personalized to you, things like this. One of the huge things we'll talk about areas is game playing. So how many of you have heard of Deep Blue? Good. If you haven't, we'll go over it. Great. So Deep Blue was the first AI system to win a chess match against a world champion, and it happened in 1997. And its play has been described by chess masters as intelligent and creative, which is interesting because they didn't describe it as foreign and an alien or something like this, right? Which you can imagine being the case. It was able to compute 200 million, or process 200 million board positions per second. Humans, when they watched Deep Blue play, said they were able to understand the reasoning behind 99.9% of its moves. It used to take this giant specialized machine from IBM. You can now do it with, maybe this is even out of date. Maybe your phone can do it now. I'm not sure. We'll look into it. But there's some open questions here. Just because we beat the world champion as an AI system doesn't mean we should stop looking at chess. How does human cognition deal with the search space explosion of chess? It's an interesting question. So when AI researchers were trying to solve chess, or to create an AI system that could play chess very well, they noticed that the search space, which we'll cover later in this class, kind of exploded. It was giant, and that made brute forcing solutions very impossible. And but how do humans do it? Humans were doing it better than AI systems. Is this the way humans think about AI? Yes.
Well, I mean, when you think about it, you look at it does explode, but each of those moves after you've done them might be useless. So you can cancel your search at a certain sub-degree of each.
Yeah, so you can prune your search space based on the rules of the game, for instance, but it's much more difficult to prune your search space based on bad moves. Right? Because what does a bad move in chess look like?
Losing a piece that's more expensive per se than another.
But that's not always true, is it? If that's part of a strategy that has a longer horizon, right? These are things that matter. Yes?
I think a lot of it has to do with our history, remembering previous matches and previous games and strategies.
Yeah, so humans maybe look more at pattern recognition, right? Having played a lot of chess or studied the game a lot, maybe they memorize a lot of specific sequences. You know, this is an open area, but has received a lot of study. Yes?
One big part could be like thinking about what the other player might be thinking and trying to use empathy to kind of see what they're trying for, what they're trying to trick you into doing. Or
Interesting. Some kind of social aspect to it, knowing that you're playing against a person. Maybe you know that person, you understand if they're aggressive or they take risks or they feel bad because it's your first game that they know of, and so they're going to play less aggressively. Thanks, Dad. Or whatever, right? And so, yeah, that's a great point. So there's a social aspect to it as well. Okay, so in 1996, Kasparov, the world champion at the time, played Deep Blue and beat it. But Deep Blue did very well. Kasparov said famously, I could feel, I could smell a new kind of intelligence across the table. Wow, that's very interesting. In 1997, they had a rematch, and Deep Blue won. And Kasparov then said, Deep Blue hasn't proven anything. And I think if you juxtapose these two statements, you can kind of see that maybe he changed his mind a little bit, right? But recently, Kasparov actually published an article called Chess, a Drosophila of Reasoning. Does anybody know what that is? Drosophila?
Proof what?
Yes, exactly. And so what Kasparov says is that chess has been to AI what the fruit fly was to genetics research, and that it has been a problem that has been studied and has moved forward the field in a very important way. And so Kasparov has come around with it. So what does game playing right now look like? Well, in 2007, they solved checkers. Completely solved. In 2016, AlphaZero beat the world champion in Go. Did you guys hear about this? Very exciting. So Go itself was a much harder problem for AI than chess was, and it took a lot of time, a lot of work, and very, very impressive. So AlphaZero came along, which was the successor, or at least based on AlphaGo and also by DeepMind, that learns to win. It's more general, it's not Go specifics, there's no Go heuristics built into it, and it learns now to play chess, Go, Shogi, which is I believe Japanese chess, and is competitive with the best AI systems there are. So AlphaZero itself was developed by DeepMind at Google. It integrates three important AI tools: search-based planning, and search is something that we'll talk about a lot in this class. It uses an algorithm called Monte Carlo tree search specifically. It incorporates reinforcement learning, which is also something that we'll cover heavily in this class, and supervised learning, deep learning specifically in this case. So we will go over all three kind of these paradigms, and you'll see these over the course. So now we've talked about it for a while. So let's return to this question. What is AI? So maybe you want to change your answer. I don't know, maybe we want to refine our answers. Why don't we talk about this amongst ourselves again? Please don't be shy. Incorporate people around you if you see that they're not involved. And let's talk about this for another 3 or 4 minutes.
Okay, he said we actually, it's going to depend on the room. Like, we're not sure when. Yeah, I think so. There's a couple rooms that they reserved for theaters.
So I guess the first time is
Okay, so yeah. Just make sure that switch is flipped. Yeah, the audio works as well.
Okay.
People are watching. One Unsupervised.
You guys think you've come up with something better than last time? I mean, last time was great, but maybe we've refined it a little bit. What do you guys think? Yes?
We said predictive models that solve a problem or accomplish a goal.
Great. Yes?
Autonomous decision making given a particular goal.
Very good. Yes?
A system that can take in information, interpret that information, then act on it.
Awesome. Yes?
To steal the idea of the people to my left, a program that makes decisions based on a heuristic.
Makes decisions based on a heuristic?
Yeah.
Very good. In fact, we're going to cover heuristics in depth when we talk about search. That word has a lot of different meanings, but a lot of them are relevant in this career. And very good to people who like things too. Yes?
We can just boil it down to a sufficiently complex sequence of if statements, right?
Maybe. I mean, that actually touches on a pretty important question, which is how do you know, right? I mean, do we care about what's going on under the hood, or do we care about what it's doing? Yes?
Do AIs need to reflect on the decision-making process based on the result of the decision?
I see. So let's see if we can define that, because I'm out of slide. Evaluate previous results and reflect, or maybe modify behavior. Is that fair? Yeah. Is that useful behavior? Is there you in there? That's it? I'm not. Perfect. Okay. Great.
Wouldn't that fall on board with machine learning?
It might. Yeah, so machine learning is probably very related to AI. Some people would say it's a subfield, but that's not always the case. Machine learning techniques frequently are used to build aspects of AI systems. This is complicated to define these things. We'll go over a lot of machine learning algorithms in this class. Great. Well, yeah, I think we've made a lot of progress. Let's refine it a little bit further, and a lot of these touched on where we're going. So, for the purposes of this class, and I want to stress that this is an open question, right? What is AI is not a thing I have an answer to. Many people have many different thoughts, and they all have good reasons for them. So, but for the purposes of this class, we'll talk about the science of making machines that, and then it'll be in one of these four squares. So, think like humans. Does this seem right? I mean, it might be, a lot of people think this is the case, and operate under this assumption, and that's great, and they do a lot of very interesting work. So let's ask the question, what does it mean to think? How do you think as a person? A lot of this involves studying the brain, maybe putting people into fMRI machines or something and looking at what parts of their brain light up when they do interesting things. We don't have MRIs available for your labs, so we'll have to do without. Well, we talked about this. Maybe it doesn't matter how the system's thinking. Maybe it matters the results that the system's getting. So maybe we want systems that act like humans, right? And some people study this, and that's great too. Yes?
Wouldn't that be the worst possible result of AI? Yes.
Well, so I think it depends on what you're talking about. That's a great point. That are we limiting ourselves to trying to create systems that perform like humans? Are humans the best at the things we're asking these systems to do? Probably not, always, right? So maybe how humans act is not what we'll study here. What if we said that we're interested in making machines that think rationally? Maybe, but again, I'm not sure that it matters what's happening under the hood. I'm not sure that we care about exactly how it's making the decisions, but maybe we care about how it acts. Yes?
Is there rationality for, like, so
all depends on context, right? So,
It does, depending on your definition of rationality. And we're going to define it here in a second for how we're going to use it. So we're going to focus here in this class on the science of making machines that act rationally. So we're interested in the techniques that produce good results, but we want to make a system that acts rationally. So what is a rational decision? Well, where does the word rational even come from? So here meaning reckoning, calculation, reason. We're going to use the term in a particular way. What we're going to use it to mean is maximally achieving predefined goals. So, as I mentioned, we're only concerned with what decisions are being made, not really the thought process behind them, although we're going to have to study how to do that in order to make these things. Our goals are going to be expressed in terms of the utility of the outcomes. So the agent does some action. What is the utility of the outcome of that action or set of actions or sequence of actions? And being rational here means maximizing your expected utility. So you may instead call this course computational rationality under this definition of rationality. So this is kind of how we're going to think about it. Yes?
So we use this definition of rationality to essentially do the supervision of the learning, right? For these AIs that we're learning, or is that?
Maybe, yeah. So if you have some supervised learning technique and you're trying to train it, yeah, oftentimes what you're trying to do is create a system that maximizes its utility in minimizing its errors. Okay, so if you take one thing away, we want systems that maximize their expected utility. That's what we're going to work on in this class. So we're going to design rational agents under this definition. So what is an agent even? An agent is an entity that perceives and acts. So some of you touched on this in the discussion that we had a minute ago. It takes as input some sensed environment. It does something in this question mark box here. And then it tries to affect some change maybe on its environment. A rational agent then is one that selects actions that maximize some notion of utility. How best you go about selecting rational actions is going to be characteristic of how you're perceiving the environment, what you're perceiving, what the environment looks like, what your action space, the things that you can potentially do to act upon your environment are. All this is going to dictate how you actually go about doing this. So more generally, this course is about general AI techniques for a variety of problem types. Artificial intelligence is a gigantic field. There's no way that we can cover all of it in depth in this semester. So what we want to do is expose you to a variety of techniques, a variety of application spaces, so that you can kind of get an idea of what the field is, dig deep into some of these things, and know where to look for the rest. And then what we also want you to be able to do is learn to recognize when and how a new problem can be solved with an existing technique. So how to take some abstraction that we've been working on, like the graph abstraction that we can search over, and how to fit your problem into that so that then you can use the search techniques that we'll describe in the next couple weeks on that problem, for instance. Okay, so here is the current plan for the course topics, broken into 3 parts. We have making decision. We'll talk about search, as I mentioned, constraint satisfaction, uncertainty or adversarial search, logic-based planning. We'll talk about making sequential decisions under uncertainty. So we'll do things like Markov decision processes. We'll look at reinforcement learning, hidden Markov models. We'll talk about reasoning under uncertainty using probabilistic models, probabilistic graphical models, decision theory, POM-DPs, partially observable Markov decision processes, and supervised learning. And then throughout the course, I'm going to try very hard to tie this to interesting applications to show you how these things are being used kind of on the forefront of the field. Okay, so a little bit of a review on the mechanics of the course. Many details on the syllabus. By the way, you can now see the course schedule, I hope. Let me know if that's not the case, but I believe you can. Also, the video is live. You'll send out the website or how to get to it, right? Great. There will be a Project Zero coming soon. I hope to have it published before the next class. It's a very simple Python intro. I mentioned that for most of the projects you can work in pairs. For this one, please work individually. There are going to be a set of additional programming projects in which you can work in pairs, as I mentioned. There's going to be a set of a set of homeworks every other week or so. You're going to upload PDFs for this. And then, as I mentioned, there are going to be short multiple choice style quizzes on Canvas roughly once a week. Okay, I'm going to do my best to post my lecture slides before the class. online for you. And then if we modify them like we did today, I will replace them or upload a second version, one of the two, afterwards. If I don't do it, I'm very sorry, I'll try my best the next time before class. It'll definitely happen after class, so I'll do my best. Sound good? Yes?
With the assignments that we can work in groups of 2, are they going to be graded differently or have like different workloads?
No.
Depending on.
Yeah, so it should be rough. I mean, it will be identical to the project. There will be like written questions, kind of self-assessment and reflection on the project that you'll have to do individually. But kind of the coding part can be done in a group, but it'll be identical. Yes?
And we will be responsible for finding our own partners?
Yeah, so the partnering system will kind of happen through, I think I'm going to use the groups setting on Canvas, so you can make groups, propose groups, that kind of stuff. Okay. Next time, we're going to start talking about search. Please do the readings. And are there other questions before we pack up?
You recommend us to start installing Python on our computers?
Well, so the installation of Python will be part of that first project that we covered there. Okay, thank you all very much. We will see you on Thursday.
You are in my AC class. Yay.